Let's start our discussion of conductors. This purple bar represents a plate of metal that's coming out towards you. Now we know that in a metal, electrons are free to flow. And this next part I can't prove without teaching you about Gauss's law, and I've tried year after year to go there, and it takes too much time, and I don't get all the way to home base. So you're going to have to trust me on this. I hate saying that, but this is one of the few times I will. The electrons in a metal very quickly get to their happy place and stop. They get to what we call equilibrium in 10 to the minus 16 seconds. Now see if you can blink in 10 to the minus 16 seconds. No, you were too slow. You're way too slow. Okay? So, if you're patient enough to wait 10 to the minus 16 seconds, no matter how you started out, the electrons will all be in their happy place. Now suppose I just dump a great big bucket of electrons onto that metal. Well, they're not happy there. You know they're not happy there. And so they want to get away from each other, and they're going to end up on the surface, on both surfaces. Now if I call sigma naught the total charge over the area of that plate, then each of those sides is going to get half of that sigma. Right? Half the electrons went to the left, half went to the right. Now if I look at an electric field, the total electric field inside the metal, and it doesn't matter where I look inside the metal, I picked a location dead center, but it wouldn't have to be. I have two contributions. I have a contribution to this due to this negative sheet that is to the left towards the negative. And the size of that is given by this formula for a single sheet of charge. If I look at the contribution due to the charge on the right, it's the same size, but in the opposite direction, towards the negative. And I get an E field inside the metal that is 0. And that's the bottom line. The E field inside of a metal, if you wait 1 times 10 to the negative 16 seconds, is always going to be 0. If it were not 0, I mean, these are just the excess electrons that I threw on that metal. But the metal has billions and billions of electrons. If the electric field were not 0 inside that metal, electrons would still be flowing. And what we find is that after 10 to the minus 16 seconds, they're in their happy place stopped. Now, this is true not just for this symmetric case, but for any metal of any shape. You could have a metal statue of some war hero, and everywhere inside that metal, your electric field has to be 0. Now, we call this electromagnetic shielding. Now, we know that electric field lines are born on positive charge, and they die on negative charge. And so that means if I have a neutral metal ball, I'm going to have electrons swim over to this side in between these plates so that they can kill the electric field lines. I have just as many positive charges over here giving birth to field lines so that they can continue on. But inside the metal, there would be no field lines because there's no field. Now there's a second characteristic of this shielding, and that is that electrons are free to move around the surface of a metal. So if I had an electric field that had a tangential component, if part of the electric field was tangent to the surface, it would push electrons, and electrons would still be moving. They would still be trying to get to their happy place. So that means that once the electrons are in their happy place in equilibrium, all electric fields have to come into that metal at 90 degrees. Now this has very important consequences when we get to lightning rods next week. We'll find that this single principle determines why lightning rods have to be sharp. Okay?